Assalamu alaikum students. Today's topic is going to be about centripetal force and centrifugal force. Let us study about centripetal force. If an object has no force acting on it, it will continue to move in a straight line at a constant speed. Let us consider this body right over here moving in a straight line. It will keep on doing so unless external force acts on it. Now, if the body is moving in a circular motion, then this is the necessary condition that it must have a radius r, which is over here, and it compels the body to move in a circular motion, and r remains constant. This is r represented the radius, and it must revolve around a certain point, which is c. If we leave the ball at certain point, then it will keep on moving in a certain direction with a velocity v, which is making a tangent at that point, making a 90-degree with the radius. If we move the ball to a 90-degree still, again it will make a tangent and 90-degree with the radius. Again, in this case, the velocity makes a 90-degree and a tangent with the ball at each and every point on the circle line, and back again. From this whole revolution, we have understood that if an object is moving, if an object is moving in a circle or along an arc of a circle, it follows that must be a force acting on it to change its direction. Moving in a circular means the direction of motion is constantly changing. This in turn means the direction of the force is constantly changing. That means the force at each point over here, over here, over here is constantly changing its direction. Now, in order for the object to move in a circular path, the force must always be acting towards the center. That means in all of these cases, the force must always act towards the center, like this, in each and every case. When we turn around a corner or around an arc using a motorcycle, car, etc., we compel the body to move in a certain motion or such a motion. The force which compels the body to move in a circle is called a center force, seeking center force, or centripetal force, which is the same thing. The body or the force, basically the force which compels a body to move in a circular path, is known as centripetal force. Now, from the next paragraph, it says, from figure we can see, that each instant and at each point, the direction change in velocity of the body produces an acceleration directing towards the center of the circle. That means because the velocity magnitude was constant, but the direction of velocity is changing at each and every point, so there must be an acceleration. Such an acceleration is known as centripetal acceleration of velocity of body changes. That means whenever there is a change in velocity with respect to time, we are compelled to say that there is an acceleration. And over here, such type of acceleration, which is moving in a circular motion, is known as centripetal acceleration. Now let us define and derive how the centripetal acceleration actually works. So here we have a circular motion of a body. First it goes to 90-degree, then 180, then 270, and then back to 360 again. In figure, consider a body of mass m moving in a circle of radius r with a uniform speed v. C is the center of the circle. Now, in this case, we have a radius which is represented by r right over here, and there is a center point C, and here is a mass m which is attached to the string, and here's the velocity of that body. Now, in this case, let's assume that this is the radius r and the velocity at this point at this instant is v1. At point A, let's call this at point A. At point A, time t1, the velocity of the body is v1. At point B, at time 2, the velocity of the body is v2. Let's move from point A to point B like this. Now, as we can see, the direction of the velocity from point A to this point, point B, the direction of the velocity has changed, whereas the radius remains constant. And there is an angle theta between the two distances. The distance from here to here, from point A to point B. Now, in this case, we call this small distance S, or the arc length. So, a body moves from point A to point B. In this whole process, it covered a distance S, and the angle which it made is theta. And the velocity, as you can see, is v2 because it changed its direction at that point B. Let us now draw a triangle PQR such that PQ is equal to the parallel of V1, PR is equal and parallel to V2, as the speed is uniform. Now, in this case, he's saying that speed is uniform. That means the body which is moving in the circular motion is moving with a constant velocity or speed. As speed is uniform, hence v1 is equal to v2 because both the velocity magnitudely are same in magnitude, but they are different in direction. So in this case, the magnitude is same, but the direction is different. By vector diagram is the delta v is equal to v2 minus v1. That means the change in velocity of a body in time interval delta t, that means t2 minus t1. That means the change in velocity in this whole time was basically observed, and the direction as well. The vectorial diagram basically will be shown later. When the delta t is smaller and change delta v is also small in the case of arc AB, approximately equal to the chord AB. That means it's so small that this curve is not shown. This is a straight line now. So if this is a straight line from point A to point B, then it is a displacement in this case. On comparison, we'll see that triangle ACB and triangle PQR are isosceles triangle, and so these are familiar. That means familiar or similar in this case. Now let us separate these uh, two vectorial diagrams so that there is less confusion. Let us separate the first triangle over here onto the side and the second triangle of the velocity over here. Now, in this case, we'll see that these two triangles are similar. Let me make them more similar by rotating. Let's say this is PQR triangle of the velocities, and this is A, B, and C triangle. Now, let's make them sim to each other by just rotating. So now you can see that delta V is quite similar to S, V2 is similar to R, and V1 is similar to R as well. Now, as you can see, this side of the triangle, as you can see over here, this side of the triangle is similar to this side of the triangle is similar to this side, and the white side is similar to white side as well. Now, in this case, we can see that these two are isosceles triangles because we know that this velocity and this velocity are both equal to each other in magnitude. V2 is equal to V1, so we call them V. So that is why we are calling them isosceles triangle. What is an isosceles triangle? Any triangle which has two sides equal to each other are known as isosceles triangle. By geometrically, we can compare these two triangles. We say arc AB, which is over here, arc AB, this one, over AC, this one. That means S over R is equal to QR, which is over here, delta V, and over PQ. That means this one. So we are taking the one side of the triangle and dividing it onto the other side, just as we are dividing the one side of the triangle, dividing by the other side as well. Now let us name the triangles. So we can say now that arc AB can be written as S, we have written as S, and AC can be written as R. QR can be represented as delta V, whereas QP can be represented as V. Now, in this simple case, we have a ratio formula that S over R is equal to delta V divided by V. Condition: when theta is very small, or delta t, that means t2 minus t1 is very small, B point will be very near to point A and then. Now, if we consider this mass to be changing its direction, but with very short period of time, that means it was here and after few milliseconds it's over here. So the theta value is going to be very small. So we can say now this S, instead of a curve, is now a displacement. This S is now a displacement, straight line, and that can be represented as S is equal to Vt. That means distance is equal to velocity into time. We have that formula. So the above equation becomes S, or distance, is equal to velocity into time. Here we have S, so instead of S we can write it down as S will be written as V into delta t divided by R is equal to delta V divided by V, provided that the delta t is very small. Now in this case we have delta V over delta t, or we can say V square over R. So how can we prove it? Just take this equation, V into delta t divided by R into delta V over V. Now if we take this t to the other side of the equation, it will be V square over R is equal to delta V over delta t. And this is how we can, by rearrangement of the equation, we are able to get this value, that delta V over delta t is equal to V square over R. And by the process of definition, we can say acceleration. If we remember that the definition of acceleration was A, that means acceleration is equal to rate of change of velocity. So delta V over delta t. So instead of writing delta V over delta t, we can also say by the definition of acceleration that if the distance is very small, or we can find the time very small for which the body is moving, then the limit delta t, which approaches 0, delta V over delta t will be equal to instantaneous acceleration. Here A, I, and S, this value stands for instantaneous acceleration, this one. So well, we can say acceleration at this point is represented by A, I, and S. Now we can also say instantaneous acceleration is equal to V square over R, because we already proved that delta V over delta t is equal to V square over R. Acceleration is also called centripetal acceleration. That means this acceleration, instantaneous acceleration, is also called uh, centripetal acceleration. So here we have the formula for centripetal acceleration, which says centripetal acceleration AC is equal to V square over R. So this is the formula for centripetal acceleration. Now, what about the force in this case? For this, let us revise what we have done in this case. We have basically made two triangles from which we have calculated the values of delta V over T, which turned out to be V square over R, and we called it AC, that means centripetal acceleration. V square, that is unit vector R over here. Now, what is a unit vector? Unit vector basically is the ratio between the vector r divided by its magnitude. It only has direction, it does not have any magnitude, or magnitude is taken to be as 1 in this case. Now in this case, AC is equal to V square over R and to unit vector R. Here R is the radius vector directing outwards from the center of the circle from the figure. That means it is moving with the radius in the outward direction. That means some force is applied on that. We see that AC and R are oppositely directed, so we can write it down as AC is equal to minus V square over R into the unit vector r multiplied by magnitude r and divided by r. So this is a mathematical process over here. We are multiplying it, as we can say, by 1. So because these two will basically cancel, so it doesn't make any difference in the equation, but it basically changed the shape of the equation. And why there is a negative sign? Because the acceleration is always towards the center, whereas the distance or the radius is acting in the outward direction. So as you can see, the acceleration and the radius both are in opposite direction, and in physics we know that the direction is represented by a negative sign. So that is why they are saying, we see that AC and R are oppositely directed, so we write it as AC is equal to minus V square over R into unit vector r into magnitude of r divided by magnitude of r. Now AC is equal to minus v square over r square, because these two r's will multiply right over here. These two r will multiply, they will make r square, and the unit vector r and the magnitude r, just from the formula we can say the unit vector was basically equal to the vector r divided by the magnitude of r. When this magnitude goes to the side, it will be unit vector r into magnitude of r is equal to r vector. So instead of writing like this, we can now write it like this: v square over r square into vector r. Now, the direction of each instant is perpendicular to the velocity and directed towards the center of the circle, as shown in figure. Now, in this figure, let's say call it 5.8. Using the previous article, which we have understood that if we have theta is equal to r s over r, or we can say s is equal to r theta. If we divide t on both sides, we get velocity on one side and omega on the other side. That means rate of change of angular displacement is known as angular velocity, which is omega. From that point of view, the previous article said that v is equal to r omega, where omega is the angular velocity of the body moving in the circle. Then in the angular form, from the centripetal acceleration, we will have, instead of putting v square over here, we are going to put omega square r. Now how this comes into being? So AC is equal to v square over r square into r. So AC is equal to, instead of v square, I can put r omega whole square divided by r square into vector r. Here we have r square omega square divided by r square into r. This r square and this r square basically cancels out. So AC is equal to omega square into r, and the negative direction between the radius is represented by the negative sign, and that is how we get the value of AC is equal to minus omega square into r. So we have the value AC is equal to minus omega square into r. Using the second Newton's law, which said that FC, that means centripetal force, is equal to MA. Or we can simply say, when a force is applied on a body, the body moves in the direction of the force with some acceleration, which is in the direction of that force. Now, in this case, if we put the value of this A in this second law of Newton, because we said that there was some force compelling the body to move in a circular path, and now we are going to find out that force. If FC stand for centripetal force and A stand for centripetal acceleration, which says that V square over R. Now if we put this value also in this equation, for this value it will be linear acceleration, but for this case it will be angular acceleration. So we'll take the two values again and try to put the values in this formula. This formula is very important, as we know the second law of Newton. So when we put the values of AC in this formula, we get centripetal acceleration, we get Fc is equal to mv square over r. That means if we put the value of v square over r in the formula Fc is equal to mac, you get Fc is equal to mv square over r. But if we want to put in the values of the angular form, then it will be the values of v, which is going to be converted. But this last part is showing the vectorial shape and vector form of the centripetal force, which says Fc is equal to minus mv square over r square into vector r. And the negative sign is showing that it is inwards. This force will be inverse of the circle. It will always act towards the center of the circle. Now, if we want to convert it into an angular form, what do? We just replace V by R omega, and we get, let's put it, Fc is equal to minus mv square over r square multiplied by r vector, putting the value of v, m r omega whole square, because v is square, divided by r square multiplied by vector r. Here, from here we can say m r square omega square into r divided by r square. This r square and this r square cancels out, and what we have left behind now, we have a simple formula m omega square into r vector, and this is what we have used over here in the angular form. Now let us clear this out so there's no confusion. So we have the centripetal force in a vector form as well as in angular form now. But there's another force which is a reactionary force, which is centrifugal force. Now, if the body was moving like this in a circular path, there was a force which we know which was acting towards the center of this circle right over here. We called it centripetal force. But to every action, there is an equal and opposite reaction, which was the Newton's third law. When we whirl a ball at end of a string, we transmit this force to the ball by means of the string. That means we are applying some force through the string onto the ball, pulling it inwards, thus keeping it in a circular path. That means we are compelling it to remain in a circle by pulling it towards the center. And there is a reactionary force to this force which we are applying, and that is known as centripetal or centrifugal force, which is, as you can see, in outward direction to the centripetal force, which is inverse direction, so that it can keep the body in a circular motion. According to the Newton third law of motion, the ball will react and will exert an equal force outward on the hand. This outward force on our hand is known as centrifugal force, a force fleeing from the center. That means it will compel the body to move out in this direction. But what if we leave this ball now at a certain point? If the string breaks and then the centripetal force suddenly removed, that means there's no centripetal force, then where it will go? It will basically fly away, just like as shown over here. There is now no centripetal force acting on the ball, so it continues to move in a straight line in whatever direction it had when the string breaks. The magnitude of the centrifugal force is same as that of the centripetal force, but in opposite direction. So there is no negative sign with the centrifugal force when, but the magnitude is the same, mv square over r. But if we put the negative sign over here, that means it is in towards the inward of the circle, and it is centripetal force then. So only the direction of centrifugal force can be represented by the positive sign, which is moving in outward direction, whereas the direction of centripetal force will always act inwards. I hope you enjoyed this session. Inshallah, we'll meet again. Allah Hafiz.